Water flows through a rectangular duct of width 10 mils and height 5 mils, 3 meters long. The velocity of water is 0.25 meters per second. The mean water temperature in the duct is 60 Celsius. And the duct wall temperature is 20 Celsius. Calculate the mean heat transfer coefficient. Okay, so we want H, right? And the heat flux, so we want small q. The following correlation may be used. Okay, so they're giving us a correlation already, so that means we don't have to go after the table and find out what is it's laminar, turbulent, fully developed, underdeveloped, and whatnot. Okay, so just need to plug those guys in to find also, which is very convenient. The subscript W refers to the wall condition. So you see there's a W here for Prandtl. So this Prandtl here is a normal Prandtl. That is the one that we get from the properties at the mean temperature. And this one is a Prandtl we get at the wall temperature. So in this case, the wall is at 20. So this would be Prandtl at 20 Celsius. Okay, so I've drew the problem already with my great drawing skills. In this problem, we have this duct, and in this duct here, we have water flowing through the duct, and it's coming in at 25 meters per second. Now, I'm going to pause the recording and ask you guys whether this is a free convection situation or a forced convection situation. So like you guys told me, this is indeed a forced convection situation because we have this velocity here. So we would apply all the things that we applied on the previous week, right? Everything like finding whether it's laminar, turbulent, and whatnot. But in this case here, we don't have to because it's been given to us, the correlation has been given to us beforehand. So all we need to do is find Reynolds, find Prandtl, find Grashof, and get Prandtl at the wall, apply the situation, find Nusselt, and with Nusselt we can find H, and with H we can find heat flux. Okay, so it's as simple as that. So I'm going into the water property table, which is A9, table A9, and I'm grabbing properties at 60 Celsius. Okay, why 60? Note that this says here the temperature, the mean temperature of the water on the duct is 60. So they're already giving us the mean temperature. So that's why we don't need to do 60 plus 20 divided by 2, right? 60 is already the mean temperature. So I'm grabbing properties at 60. The only one that I'm grabbing at 20 is the one for Prandtl at 20, which is our Prandtl wall, right? Prandtl W. Okay. All these properties I don't have to interpolate. The only one I had to interpolate was actually this one here. Okay. One of the things that show up is on the very right column, the thing I told you guys to pay your attention to, which is this chunk of constants here. And that chunk there is a bundle that if multiplied by our characteristic length to the third times our difference in temperature gives us the Rayleigh number. You don't have to memorize this either, but you can look on the actual table, on table A9 on the top corner, you'll see that this is there. This information is given there. Okay, and why is that important? Because that means that first of all, it has beta, which we can't grab beta for the water unless we use something like this or grab it straight from a table. And second of all, it makes our life to calculate Grashof easier, because if this is true, then it means I can calculate Grashof by doing this thing that comes off the table times this divided by Prandtl, right? Because if this is true, right? So all I did was this. Sorry, I don't know what I'm going to do. All I did was this, right? If that's true, then Grashof is just the same thing divided by Prandtl. Okay, so that's the way we're going to calculate Grashof in this problem, given that we can't calculate beta any other way. All the information that we need other than that is there. But let's start with calculating Reynolds. Let's first calculate Reynolds. And we know Reynolds is density, velocity, characteristic length divided by the viscosity, and we don't know this guy, right? So that's precisely where our hydraulic diameter is going to come into play. The hydraulic diameter, if you guys recall, For this case here, it will be 4 times A plus B. In this case, the A, B are the height and the width of this duct here, and divided by the perimeter. Perimeter is 2 times the 10 plus 2 times the 5, so it's 2 times 10 plus 5. Yeah, so let's calculate hydraulic diameter so we can plug into our Reynolds. That will be 4 times 5 times 10 to the minus 3 multiplied by 10 times 10 to the minus 3. Note that I'm putting everything in meters. And that will be divided by 2, 5 plus 10 times 10 to the minus 3. Okay, so our hydraulic diameter is 6.6 mils. And that's exactly what we're plugging here in Reynolds. Here we have 900, what's the density? 983.3. Velocity 0.25. Hydraulic diameter 6.66 times 10 to the minus 3. And this is, whatever that was, 4.71 times 10 to the minus 4. Reynolds is 3,476. 746. Sorry, no, that was right, 476. Okay, so we have Reynolds, we have Prandtl, we have Prandtl wall. The only thing we don't have is Grashof, so we can grab Grashof and find Nussel. This guy here, the big chunk from the table is 6.48 times 10 to the 10. Okay, again, this is from the table. I didn't do any math to grab this. Characteristic length, hydraulic diameter, right? So 6.66 times 10 to the minus 3, and now have this third. Delta T, what is my delta T? 60 water and 20 wall, so 40, right? 60 minus 20. And I'm dividing everything by Prandtl. And Prandtl is 3.01. So Grashof is 2.54 times 10 to the 5th. Brilliant. Let's find Nussel. Point 17 times Reynolds to the 0.3. Reynolds is 3,476. 3. Times Prandtl to the 0.4. So Prandtl is 3.01 to the 43. Let's go ahead with a new line here so that we're not running over each other. Times Grashof to the 0.1. Grashof is 2.54 times 10 to the 5th. That's the 0.1. Times Prandtl over Prandtl wall to the 0.25. Okay, so that means Nussel equals, what did I get? 11.32. And we also know Nussel equals convective coefficient, which we're looking for, and times what? Characteristic length, right? So in this case here, it is the hydraulic diameter. H is, I don't want to use, I'm going to use red for this. H is 1,000, 1,100. And 11. 0.6 watts per meter squared Kelvin. That is one of our answers. We're looking for the convective coefficient. That's it. The other thing we're asked for is the heat flux, right? Heat flux being simply Q over A, which is simply this, right? So that'll be 11.6, and this is 60 minus 20. This is 45.5. Okay, so this is more a question to introduce Grashof than anything else. But before we go, because this is the solving of the problem, but before we go, what I want to do is 44, not 45, sorry, 44. There you go. Before we go, I want to actually find Q with you guys. I want to find Q. Okay, because we know Q is, you can just get small q multiplied by area, right? But in this case, our area is a bit different because our area is not, like before, it's not a cylinder or a flat plate. Our area involves this guy and this guy, right? And we have two of them, one on the bottom, one on the top, and then one on the left, one on the right. Two of each. So our area is, let's draw our areas. We'll have a smaller one. We have the one that I drew in yellow and the one that I drew in blue. The one in yellow being 3 meters long and 5 mils. And this one being 10 mils and also 3 meters long, right? And we have two of each. So the area here is 2 times 3 times 5 times 10 to the minus 3 plus 2 times 3 times 10 to the minus 3, right? And this simply put is 6, 5 plus 10 times 10 to the minus 3. And so that's 0.09 meters squared. So that means that my Q is 44.5, 0.09, about 4. Yeah, so I just wanted to do this because you have a different area now than you're used to, so might as well do this. Any questions?